Good evening to one and all. On behalf of the Department of Electronics and Telecommunication Engineering and the entire organizing committee. Madam, am I audible?
Yes, sir, you are audible. Please continue.
Sorry. Good evening to one and all. On behalf of the Department of Electronics and Telecommunication Engineering and the entire organizing committee, I, Mr. P.N. Ghate, extend a warm and heartfelt welcome to our resource person, faculty participants, research scholar, and dear colleagues to the Day 2, Session 3 of the AICTE Atal-sponsored 6-day online faculty development program. I welcome today's respected speaker, Professor Anil Kottan Tharail, sir. Professor Anil Kottan Tharail received the BTech degree in Electronics and Telecommunication Engineering from the National Institute of Technology, Calicut in 1993. The MTech degree in Electrical Engineering from IIT Bombay in 1997. The doctorate degree from University of Bundeswehr, Munich, Germany in 2002. From 2001 to 2006, he was the Inter-University Microelectronics Center, Leuven, Belgium, where he worked on FinFETs, Metal Gate, and high K integration in logic technologies. Since 2006, he has been the Department of he has been with the Department of Electrical Engineering, Indian Institute of Technology, Bombay, where he is currently the Bank of Baroda Circular Economy, Green Energy, and Sustainability Chair Professor. He has authored or co-authored more than 150 papers and conference presentations with H index of 36, and he is an investor, co-inventor of more than 10 national and international patents in these fields. 27 students have completed their PhD under his guidance. He is a distinguished lecturer of the IEEE Devices Society and the fellow of the Indian National Academy of Engineering. He was the head of the Center for Research in Nanotechnology and Science and the Sophisticated Analytical Instrument Facility, SAIF at IIT Bombay during the June 2018 to December 2021. Currently, he is a professor in charge of the Photovoltaic Technology and Innovation Center, POTIC at IIT Bombay. His research interest includes the silicon solar cells, application of graphene electronic devices, CMOS device physics, design and modeling, material for advanced CMOS devices and solar cells, electrical characterization, gate offset, reliability and hot carrier effects, radiation effects in MOS devices. Sir has many sponsored consultancy projects in his credit. Sir has been awarded by many prestigious awards and honors. Sir is also associated with many professional activities. Thank you, sir. Sir, I request you to start the session.
Thank you very much for the introduction, and I'd like to thank the organizers for inviting me to give this lecture. Am I audible?
Yes,
Yes,
sir.
sir.
Okay. So let me share my slide. If you can allow me to do that. Yes. Can you see my slide presentation?
Yes, sir, it is visible.
Okay. Yeah. So I'm going to talk about the silicon. I'm sorry. Yeah, so I'm going to talk about the silicon solar cell technology. And I saw in the program yesterday, Dr. Sushil Kumar from NPL had probably talked to you about the design of solar cells. And he also has been working on silicon solar cells for many years. So I don't know how much of content he has already covered. But anyway, so in teaching, it's not a bad idea to repeat some of the things so that you get your concepts clearer. So with that as a brief introduction, so I'm going to talk today about this topics. So what is the context of PV technology and why is it important and interesting today? And then we'll try to basically understand how a solar cell works. So this part is essentially true for any solar cell. with some material specific variations of the basics. And then we will look at solar cell implementation and design of silicon solar cells. And if time permits, I would also talk about some of the advanced solar cell structures and how these are characterized. Okay, so what is the context of PV? So you can see the climate change has been a prime driver for not ongoing transition in energy sector. So you can see that, we are using more and more of electricity, and we are actually producing this from meaning non-fossil fuels and so on. And this is mainly driven by the fact that fossil fuels emit greenhouse gases, and that leads to climate change, and which is quite visible to many of us, right? And you can see the as a consequence of this developments, cumulative global PV installations by mid 2025, so middle of last year, was 2.5 terawatts. And if you look at the next point, global solar and wind produce more electricity than coal in the first half of 2025. So this is a major milestone. And you can see only about 21% of global energy consumption is in the form of electricity. Okay, so that's a very important thing to keep in mind, because when we talk about electricity, you have Ministry of Power and so on and so forth. But if you look at power and energy, that's only 1/5 of the Ministry of Power is dealing with only electricity. But then we have a lot of fossil fuels for running vehicles and producing electricity itself and so on and so forth. Now, one thing that is happening in response to climate change is that, see, the electricity is very clean at the point of use. We also now have very clean methods to produce electricity. So what is expected is that electricity's share to energy consumption is increasing steadily. It's already happening. And we are expecting that this would actually go to very high levels going forward. Okay. So if you look at China, which is actually a champion in many of these technologies, in fact, in the renewable energy sector, they are actually very, in terms of manufacturing, deployment, and so on and so forth, they are world leading country. So they already have 30% of energy consumption is in the form of electricity, much more than what is a global average. And this is increasing with rapid adoption of electric vehicles, bullet trains, electrification of industrial processes, and so on and so forth. And as a consequence, the fossil fuel demand in China is predicted to peak in 2027. And many other countries are following this trajectory, and we are also actually going in the same direction. But all said, some of these things may sound very impressive, large numbers, but all said, the contribution of solar PV to total energy production and consumption today is about 3%. Okay. So if this has to become a major technology, we have a long way to go. And there are promising things happening. For example, first half of 2025, the total investments in this sector was 386 billion US dollars. And this is half of the year. Yeah. And it's actually, if you look at the semiconductor industry, ICs and so on and so forth, right? Their half yearly revenue is actually smaller than this. So PV industry is huge from that perspective already, and it is predicted to grow exponentially going forward. So PV is accounting for 80% of the renewable capacity additions in the first half of 2025. Yeah, 80% of the renewable capacity additions is very, very important to understand. There are other renewable technologies, but PV is actually the leading renewable energy technology. And you can see this graph from this consultancy called Ember. So this is the renewable generation of electricity. Then you have the coal, right? So you can see in the first half of 2025, renewable produced more electricity than coal, which is a very important landmark. You can appreciate that if you look at, the couple of years ago, what was going on. right? 10 years ago, this portion was very, very low. Now, if you look at the global installed capacity, electricity capacity, generation capacity, you can see this is like coal, natural gas, wind, and hydropower, and other things, nuclear, and so on. Solar is now the leading total installation, but total installation is somewhat misleading for solar in the sense that coal-based power plant can be operated 24/7. Whereas solar, only when sun is shining, you can produce electricity. But still, this is a significant milestone um, as of now, right? Now, considering all these things, Science Magazine, one of the most reputed journals in the science field, announced this year 2025 as the year of renewables. Okay, and you can see this kind of celebrations by leading newspapers and science magazines, technology journals, and so on and so forth. Now, what is happening in India? So we have a cumulative installed capacity of 132.8 gigawatt of solar PV till 30th of November 2025. And out of this, so actually you can see almost 25% of that or 20% of that was installed during the previous 8 months. Okay, so 1/4 of that, this number was installed just in 8 months, whereas this installation started picking up in India from 2010 with the National Solar Mission announcement. And the capacity is expected to increase to 300 gigawatts and more by 2030. Okay, so we would actually, increase, in the next 5 years, we are going to add a lot more than almost double of what we installed in the previous, meaning last 15 years. Yeah, 5 years we are going to install double of what was installed in 15 years. And if you look at the electricity demand, just electricity demand, about 7% of electricity demand in India is supplied by solar PV. And you can see one of the reason is also the lowest tariff. So actually, the solar is now the technology that produces the lowest cost electricity. And of course, this is only available during sunny days and sunshine hours. So you need some storage. So if you combine battery storage, at price of 2.7 rupees per kilowatt hour was discovered in an auction in Madhya Pradesh in September 2025. So, which means that cost competitiveness is now an important driver for solar PV deployment. We started off saying climate change, but there are some governments, for example, in the US, Trump administration is actually trying to discourage renewable energy, but people are actually buying a lot more solar because it's become economically much more competitive than any other electricity generation technology. So it looks like this deployment going forward is unstoppable, the growth of the deployment. And in fact, that is the reason why nature, so nature celebrates this last year as the year of renewables. And we, of course, have significant manufacturing capacities in the country. So we are not just deploying it, but also manufacturing. You can read these numbers here. But one thing that is very clear is a lot of things are happening in India.
Sir, please unmute yourself. Hello, sir. Will you please unmute yourself?
Oh, you could not hear me?
Now you can.
Yes, sir. Okay. Now it's so. Yes, sir. Okay.
No, I don't know what happened because I asked whether you can hear me and I started when you said
Sir,
yes.
actually, somebody was making a noise in the background, so administrator
muted everyone. So sorry, but please continue.
Okay. Okay, so yeah, sorry. Okay, so you can see significant manufacturing capacity is being added. Now, if you look at the contribution to electricity generation from wind and solar, so what is even predicted? So going forward, I told you about what is going on or what has been going on, but now if you look at this, people are predicting that the electricity generation contributions in 2024 less than 20 percentage. That's going to get close to 50 percentage by 2035, especially in China. So half of all the energy used would be coming as electricity, and most of that would be produced by electricity, meaning by photovoltaics, right? And you can see this paper from so 2023 or so, where they're actually predicting that the total installations would exceed or come close to 100 terawatts from about 2.5 terawatts in the next 35 years. So a 40-fold increase in the installation of PV. And this is going to be a huge industry going forward. So as teachers and so on, we are actually, of course, a lot of people will be needed to implement this transition, and engineers especially, and we have a responsibility to train such engineers, and this workshop is very timely in that context. And what I would like to show here is actually from paper where they have done these predictions, right? So these are predictions from the World Energy Outlook reports by the IEA, International Energy Agency. So they have been predicting very conservative numbers, projections, right, for solar PV deployment. The actual numbers are here. Yeah, so you can see there are huge deviations. So actual is going much faster than what anybody is predicting. Okay. So these predictions that I showed you may be already underestimates of what is going to happen in the sector. Now, why this is the sector is picking up, and you can see the conversion efficiency of solar technologies have reached close to 30 percentage. Yeah, this is what is called a Shockley Quasar limit for the solar cell efficiency of what is called single junction solar cells. So that depends on the band gap of the semiconductor, and it can reach close to 31 percentage. Okay. And practical solar cells today that you can buy in the market are giving you close to 25% efficiency. But recently also solar cells with 27.8 percentage efficiency has been demonstrated by these companies, Longi and Jinko. Both are Chinese companies using two different silicon solar cell technologies. Okay, so I'm focusing on this because I'm talking about silicon, but also these are very large area devices, okay, stable technologies. So this is solar cell, but then you need to make what is called a solar panel. That's what you will see on the rooftops and so on, right? Meaning a solar panel would have several solar cells in them. And there is a chart of efficiency evolution as a function of years produced by National Renewable Energy Laboratory. So you can see this is, you can already get 26 percentage efficient photovoltaic modules in the market. Meaning actually these are top end of line products, but most of the commercial ones are coming in this range. Okay. Now, of course, that is the efficiency part, and I may want to tell you a bit about this. So if you look back in 2010, for example, even though record efficiencies were about 21% or so, yeah, for the silicon technology, the market leading technologies were more or less like 13, 14%. Yeah, so we have almost double the efficiency. That is significant. And then the other reason, of course, is economics is very, very important. When you go to buy this, what is the price of these products, right? So this is very interesting graph. This is starting from 1970s. So 1976, you can see for 1 watt peak of the solar panel, you have to pay close to 140 or so US dollars. Okay. But in 2024, that number is $0.08 per watt peak. So that's a very important thing, right? You can see already more than 4 orders of magnitude reduction, right? So that is a very significant factor contributing to the popularity of the PV technology. And this has come from two reasons. One is, of course, the improvements in the technology, but also you are actually manufacturing a lot more of this. So there's something called the learning curve. So this is called a learning curve, learning rate, and so on. So as you use more and more of a technology, more revenue is generated by industry. They will put more of that money into research and development and also manufacturing capacities. So the unit production cost actually decreases. And this is a very, very important positive cycle. So cost keeps on reducing as the manufacturing capacity increases. Now, if you want to keep yourself updated about the record efficiency of solar cells and modules, there is this very nice paper which is published every 6 months by the lead author for these papers are Professor Martin Green from UNSW, Australia. Version 66 was published in May 2025. I think this month, version 67 would actually be published. So, and this is in open access. You don't have to pay for the subscription. And you can see what are the latest numbers on record efficiencies. Okay, so I think I have tried to convince and I have been successful. I hope that PV technology is a very important technology and a huge industry is going to be built based on this. And now we will see how this whole technology works. Okay, so for this, we need to go to a little bit of physics of solid state materials. So I will keep this very brief. You probably know that about this materials class called semiconductors. And they are actually, in terms of conductivity, they are somewhere between insulators and metals. Okay, so typical examples are silicon, gallium arsenide, and so on. So most of the integrated circuits, ICs, are made on silicon. And there are specialized high frequency circuits and some infrared LEDs and other things being made using gallium arsenide. And you can see what is called a band gap or band structure. So what this shows is essentially the energy levels that electrons can actually occupy in the electronics structure of this. So you see this, there are two bands, two sets of bands. So this is one band, and separated by an energy of Eg, there is another band. Okay, so this top band is called conduction band. This is called a valence band. Yeah, and this gap is called the energy gap or band gap. And at absolute zero, all the electrons in the material would be in the valence band. Okay, and they will be actually bonded to the silicon. We will see that in a short while. And no electrons would be available for conduction because they are actually participating in chemical bonding. Okay, so they are not free to move around, and hence no conduction is possible. Yeah, so at absolute zero, semiconductor usually will be non-conducting. But then if you, by providing energy, you can excite these electrons to higher energy levels. So we will see that in a moment. And those electrons can move around. Okay, so that provide the conduction. I will not go into the difference between these two, Of course, you can see some differences, right, between silicon and gallium arsenide. But there are some important implications for different kinds of applications. But we will not go into those details. The band gap is also temperature dependent, and that's a very important consideration. You can see as the temperature increases, the band gap decreases. So that is important because the efficiency of the solar cells also decrease with increasing temperature, and that can be traced back to the temperature dependence of the band gap. Okay, so for common semiconductors, this is true. But more recent ones like perovskite, for example, shows a slightly positive band gap, meaning temperature dependence of band gap. So the band gap in those cases increase mildly with increasing temperature. Okay. Now, if you look at the semiconductor, we have, you can classify this into intrinsic and extrinsic, especially for silicon. So you can see here, this is pure silicon. You can find each silicon atom is bonded with 4 neighboring silicon atoms, and you know this, the valency of the electron is 4, and these 4 electrons are actually shared in covalent bonds with 4 neighboring silicon atoms. So at absolute zero, none of these electrons are free to move around, and hence no conduction is possible, right? But on the other hand, now you actually introduce phosphorus or boron and similar dopants. So basically substitute a silicon with phosphorus. So the phosphorus has 5 valence electrons, 1 more than what you have for silicon. So that electron is actually can be easily detached from phosphorus by providing a little energy, and that is then available for conduction. Okay, so this can freely move around. Now, if you can take the case of boron, so it has 3 electrons in the valence band. So you are replacing one silicon with a boron, for example, here. So it's short of 1 electron. So there is one place, okay, energy state that is free, and electrons from other bonds can actually jump over, right? So this provides then a path for conduction, right? Electron from here jumps over to this. So you can think of a current flowing in the opposite direction. So this is called a hole. And of course, this is a free electron. And this is what is called a hole. And phosphorus is not alone. You have other group, elements with 5 valence electrons, antimony and arsenic. So these actually donate electrons to the silicon lattice, hence they're called donors. Okay, so resultant silicon is called the N-type because it has more electrons than holes. And in the case of boron, aluminum, gallium, indium, so these are acceptors because they actually accept electrons from the lattice. The resultant silicon is p-type because the hole is actually modeled as a positively charged carrier. Now band diagrams. So this is, I think, not very important, but we will just briefly discuss this. So this thing that you have seen here is very complicated, okay? And this axis is not really the space. Yeah, so this is what is called the momentum vector. But if you look at a real device, device has X, Y, Z dimensions, right? So you want to look at it from a physical dimensions of this. So we convert this, we take the bottom of the conduction band, top of the valence band, and draw that as function of distance. Okay, so electron energy increases in this direction, and the hole energy increases in this direction. Well, other details are omitted, but this is a good way to represent. So if you have, when we take students for PhD and so on, this is a very standard question to actually draw the band diagrams of semiconductor devices, PN junctions, transistors, solar cells, and so on. Okay, so I'll skip these things. Now, so we talked about the bands, right? This is a conduction band, valence band. And we want to know how many electrons are there, how many holes are there. Okay, So we want to find out this, and this is determined using these equations. So this is a concentration of electrons. How do you find this? So you actually determine what is the density of electronic states in the conduction band. Okay, so that is given by this term GC. So this is the density of electronic states in the conduction band. And now what is the probability they are occupied? So that is the Fermi-Dirac statistics. So this is actually a statistical function. And then you integrate this from the conduction band edge bottom to infinity. Okay. And then you can find out the number. So this is like, you get into an auditorium, what is the density of seats there, and now what is the probability of that seat being occupied, right? So that's the kind of calculation that we are talking about. And for holes, this is a similar calculation, but for the valence band, so this is the density of states, electronic states in the valence band, and the probability they are empty. So that is 1 minus Fe. Fe is the same thing as here. So this is the probability of occupation. So the 1 minus Fe is the probability that is vacant. So you do the integration, you can find out the concentration of electrons and holes using the second equation. Now, these things are actually known functions. People have already derived this G, C, Fe, and GV. And using that, you can actually determine the closed form equations, analytical equations for N and P for certain simplification. I'll not go into the details here, but some important aspects here. So if you take the product of electron and hole concentration, you get an equation like this. So Nc and Nv are constants at a given temperature. And we have also seen Eg, though it is dependent on temperature, if you take a constant temperature, this is also a constant. This is what is called a Boltzmann's constant, which is a constant, of course. And then you have temperature. So at a given temperature, N into P would be a constant for a given semiconductor. And now, if intrinsic semiconductor is a place where we have seen all electrons are participating in bonds, right? So what you need to do is to actually excite electrons so that they can freely move around. You need to provide energy to them. Break a bond. But when you break a bond, electron comes out, but then you also have a vacancy there, right? So that vacancy is the hole. And that means that you are always producing in an intrinsic semiconductor a pair of electrons, meaning a pair of electron and a hole. So which means that if you have an intrinsic semiconductor, N is equal to P all the time under equilibrium condition. So you can then say, okay, NP is something what is called intrinsic carrier concentration, Ni square. Okay. And then you can do the calculations of this. So this is, yeah, I think we have. So Ni for silicon is actually 10 raised to 10 per centimeter cube at room temperature. Okay, so this can be calculated. And now, based on the temperature range and other things, let's say an example for an N-type silicon material where you dope this with, let's say, phosphorus, right? Nd is the concentration of phosphorus per centimeter cube. And then you can find out the hole concentration. Electron concentration will be equal to the dopant concentration because each one of the phosphorus atoms contribute 1 electron. Hole concentration can be determined Ni squared divided by N. N is nothing but the dopant concentration, donor dopant concentration. And if you take this example of 10 raised to 19 for Nd, Ni I mentioned is 10 raised to 10. So Ni squared would be 10 raised to 20. So you have 10 holes and 10 raised to 19 electrons. So you can see these are then called majority carriers. Yeah. And holes will be minority carriers. Similarly, for p-type materials, you get electrons as minority carriers, holes would be the majority carriers. Now, there's something called Fermi level, which is basically part of the Fermi-Dirac statistics. So this is essentially representing the balance of electrons and holes in the system. Okay. So for intrinsic semiconductor, you can see the electron and hole concentrations are equal. Yeah. So this essentially means that the Fermi level in an intrinsic semiconductor will be in the middle of the band gap of the semiconductor. Okay. So this is your EC, the conduction band bottom, valence band top EV, and EI will be the middle of this. Okay. So that can be also calculated from these equations, which we have seen on previous slides. And for silicon, the band gap is 1.12 electron volts at room temperature. And then you have half of that is 0.56 electron volts, right? Just a moment. Okay, so the position of Fermi level is also, if you now start doping the material, you can see for a p-type doped material, the hole concentration is higher than the electron concentration. So you expect that the Fermi level to move towards the valence band, and that's what really happens. This is an example of silicon doped with gallium of 10⁻17 per centimeter cube. So the Fermi level shift down from the middle. So middle is when you have an intrinsic semiconductor, right? So depending on the concentration, you can calculate what is the shift using this expression. For n-type doped material, some similar calculations you can find. In the case phosphorus 10⁻19 per centimeter cube, the Fermi level shift up. Okay. So this is a very important thing for us to understand how the solar cells work. Now, so we have a quick review of basic semiconductor physics, and then we'll go to try to understand how the light is absorbed in the semiconductor, what happens then. So you can think of what is called a generation processes. So generation of electrons and holes. So that's what we are referring to. There are mainly two methods for this. One is the thermal energy. You provide, so I said at absolute zero, all electrons will be in the valence band, right? But those electrons are not free to move around. So you want to excite them to conduction band so that they can move around and current can flow in the semiconductor. So you can break these bonds by providing thermal energy, heating up. So from absolute zero, you increase the temperature to, let's say, room temperature. Already you will have substantial concentration of electrons, and as a consequence of also of holes. Or you shine light on the semiconductor, and if the photon energy is greater than the band gap energy, then this holes, meaning the electrons can absorb the photon and jump to the conduction band. So this is called a generation, band-to-band generation process. So this is the valence band, conduction band, from band to another band generation. Of course, impact ionization is another generation process, but solar cells, we usually don't discuss much about it. Now, so we now understand photons are being absorbed if the photon energy is greater than the band gap in a semiconductor. So we can then see, okay, I have a piece of semiconductor, and then a certain light with intensity I0 is entering from one end, okay? And the light is actually getting transmitted through, and during this transmission, of course, certain amount of this light, number of photons, will be absorbed by the semiconductor. So how does the light intensity look inside the semiconductor, right? That's what we want to understand. So you can imagine that, let's say if we take a sliver of this block from x to x plus dx. So in this thickness of dx, a certain intensity of light or certain photon count will be absorbed, and that would be dependent on what is the intensity of light entering the point x. And of course, the thickness of this, right? So the proportionality constant is what is called the absorption coefficient, and that depends on the energy of the photon. So you can solve this differential equation very simple, so that actually tells us that the intensity of light as a function of x, the distance from this point in this direction, would decay exponentially. Okay. So that is telling us that, okay, you have electron hole pairs generation, and that would also decay exponentially in the semiconductor. And of course, you are taking a semiconductor and you are generating electron hole pairs. Suppose you switch off the light, what happens? So you have, these are excess compared to an equilibrium condition, right? So there must be a reverse process where the electron goes back to the valence band. So that process is called recombination. There are three different kinds of recombination processes generally seen in semiconductors. One is the band-to-band recombination. So this is just the reverse process of what we have seen, right? Electron from the conduction band just give up its the excess energy, so the band gap energy, and fall back to the valence band. So of course there must be an electronic state available for the electron to fall back. Okay, so this is what is called band-to-band recombination, and this can result in emission of photon light. Yeah, so that's what we see in LEDs, for example, or laser diodes and so on. So radiative recombination rate is given by this equation, what is called the excess electron concentration or excess hole concentration divided by what is called a lifetime of carriers. So this is the average time that the electron would be alive from the moment you turn off the light, for example. Okay, so the lifetime is defined by this expression, tau is equal to delta n, the excess electron or hole concentration, divided by the recombination rate. For radiative recombination, it is the radiative recombination rate is proportionate to the product of the electron and hole concentration. That is obvious because you need an electron and a hole for this to happen. Okay. And you have, these things can be omitted. We will go to the next thing. So we have a radiative recombination lifetime given by tau radiative recombination. There is something called Auger recombination. It's a little bit more complex. You have two electrons and hole participating in this, where this electron would actually give out its excess energy to this electron, the second electron that goes up, higher energy, okay, and this falls to the valence band, and you have a recombination. And of course, this electron is higher energy, and of course, this energy is lost when this electron collides with the atoms in the semiconductor. You can also have a two-hole, one-electron process, just the mirror of this for hole recombination. So since two electrons are involved in this, you can see n square p. Yeah, two electrons and one hole is required. So the rate is proportionate to n square p. Two hole collision process, again, the rate is proportionate to np square. Yeah? So the recombination rate is the sum of the two, and we will not go into the detailed equations for this. Another recombination process is what is called a Shockley-Reed-Hall recombination, and this happens in a very curious way. You have a semiconductor, and we talked about the conduction and valence band, and this is called a forbidden gap, which means that there are no energy states in between. But that is true for an ideal semiconductor. Okay, nothing is ideal. In practice, there are non-idealities, right? So one of the non-ideality is that impurities. We will see that in a moment. So which actually introduce electronic states in the forbidden gap. So that can lead to this recombination process. These are the names of the scientists who proposed and established this process. And you can see an electron being captured by the electronic state here, and then that recombines. So it's a two-step process, right? Electrons falls to this intermediate level, and from there to the valence band. Or you can also imagine electron falls to this intermediate state, hole is captured. right? So you have a recombination process. This usually lead to heat generation in the semiconductor. So you can see this is a band gap of silicon, and if you have any of these impurities in the semiconductor, you can get this electronic states in the valence band, meaning the forbidden band gap of the silicon. So it's very, very important for us to make silicon material which are ultra pure. Okay. So this is, silicon that is used for semiconductor and solar cell manufacturing have less than a parts per billion of parts per trillion of impurities. So that's one of the big challenges to make this. In fact, this is the purest man-made material which is widely used for industrial applications, right? Now, for the SRH recombination, you can see there are a lot of equations here. But one thing I would really highlight is that recombination rate, of course, is dependent on the electron and hole concentration, but also on the properties of the defect level that we have seen in the in the forbidden gap. So there's something called capture cross section, and I'll not go into the details, but this is very important. This talks about the density of the impurities. So higher the density of impurities, lower is your lifetime. So very important consideration. Meaning lower lifetime means what? You have higher recombination rate, right? Recombination rate is delta n divided by tau. So smaller the tau, higher the rate. So we'll skip these things. Let's get into this. Okay. Yeah. Now, if you combine all these recombination rates, you know, in a semiconductor, you can't say, okay, I have only radiative recombination. No, that is not true. If you generate electron hole pairs, then they will recombine with all this available mode methods of recombination. So total recombination rate is the sum of recombination rates of these individual processes. And then based on the basic equation, you can say, okay, this is the bulk of the semiconductor. We'll come to the surfaces in a moment. You have what is called an effective bulk recombination lifetime, and that is given by this equation. So delta n is common on the left-hand side and the right-hand side of this equation. So you can eliminate that. So the effective lifetime is given by this equation, right? And you can see the plot of this. So this is a radiative recombination lifetime, and this is the OJ recombination lifetime, and this is the Shockley-Reed-Hall recombination lifetime. And effective lifetime is most of the time for semiconductor silicon especially is decided by the SRH recombination, which means that the concentration of the defects in the semiconductor. Okay. For silicon, yeah. For materials like gallium arsenide, that story is different. So in the what happens at the surface? We talked about the bulk. So of course, if you take, this is your, let's say, silicon, yeah, each silicon is bonded to 4 neighbors. And then what about the surface? So you can see here, this silicon atom is bonded only to 2 neighbors, not 4, right? So there are 2 electrons dangling around here. So that leads to a lot of defects. So this is your bulk of the semiconductor, this is the surface, and this is your band gap, and you have defect states just because of this, okay? And that can lead to recombination. Electrons and holes can be captured by this defect states, and that has to be included in our analysis. And usually that leads to a fairly complex equation. This is also following the Shockley-Reed-Hall recombination theory. And we will not go into the details here, but how do you reduce this? So we have seen the bulk, we have to reduce the concentration of impurities, but on the surface, what do you do? Because it's not related to the impurities in the semiconductor, but rather a disruption in the crystal structure at the surface. So you can do what is called a chemical passivation, okay? So basically the surface is made to bond with oxygen, hydrogen, and so on. So for example, you can grow a silicon dioxide dielectric on top of silicon. So you have a lot of the silicon oxygen bonds that will cover the surface, right? So the interface, the density of the states, so that is represented by what is called the DIT in this equation, it can be reduced, which means that the recombination rate can be significantly reduced by doing what is called a chemical passivation. Another method is what is called a field effect passivation, and this is made this way typically by, let's say, a dielectric with some charges in it. For example, here there are negative charges. So an electric field will be set up in this direction, which means that the electrons coming to the surface of the semiconductor will be repelled by the electric field set up by the charges in the dielectric. Okay, just a moment. Yeah, sorry. So we need to take both the bulk recombination as well as the surface recombination into account to calculate what's called effective lifetime of carriers. So that is given by this equation, and we need to consider both the things. So now if you look at the solar cell, what are you trying to do in a solar cell? Okay, so we have all necessary information to learn about the solar cell, but before that, let's go to this what is called quasi-Fermi level. So we defined Fermi levels previously for n-type and p-type, but these are under equilibrium conditions where there are no excess electrons and so on. So this is under equilibrium. You can define the Fermi levels. We have seen this for intrinsic semiconductor. This is at the middle of the band gap. For n-type, the Fermi level is close to the conduction band. For p-type, it's closer to the valence band. But when non-equilibrium conditions exist, when you, for example, shine light, then you would like to use the same equation. So we define what is called a quasi-Fermi level. Okay. So we'll see for a equilibrium condition, the Fermi level for both electrons and holes are the same. But for non-equilibrium conditions, you can see the Fermi levels are different. Okay. This leads to the potential developed in a solar cell. So we'll take an example. This is a semiconductor silicon doped with donor type, so phosphorus, arsenic, and so on and so forth, of 10 raised to 17 per centimeter cube. But then by shining light, we introduce electrons and holes of concentration 10 raised to 15. This is just because of shining of light. Let's see what happens. So this is the equilibrium condition. So this is your conduction band, valence band. This is a position of the intrinsic Fermi level, just shown as a reference. But then in under equilibrium conditions, you have a single Fermi level position, right? That's close to the conduction band edge. Now you shine light. This leads to what happens to the electron concentration. So that defines EFN. So I've shown the EFN here. Why? Because EFN is the same, right? It has not changed because the electron concentration anyway in the semiconductor is 10 raised to 17. You have added 10 raised to 15 to the 10 raised to 17. 1% increase in the concentration of electrons, and that does not lead to any change in the position of the electron Fermi level. But here you can see the whole concentration is significantly increased, and that leads to splitting of the Fermi level, and you have a separate Fermi level for the holes. So this is the separation of the Fermi levels, and this is what is leading to the current, or actually the voltage, in a photovoltaic device. Okay, so we are getting closer to understand how a solar cell works. And now the last thing is what is called a continuity equation. So what this means is that you have a current. Let's say this is a block of semiconductor, and current is flowing in by some mechanism. We don't know. So a current, electron current of Jn is actually flowing in here. And through this phase set, the current is coming out. Okay. And in general, these two currents need not be equal. Yeah, because In a semiconductor, you have generation mechanism. So if you are producing electrons and holes inside this, so what is coming out could be different from what is entering this region, right? And then there are recombination. So if there is a recombination, the current could actually decrease. So that's what is actually mentioned here. So you have a rate of change of the electron concentration in this volume is essentially the difference between these two currents, and you can convert that into the number of electrons, the difference of the electrons coming out. There's certain number of electrons enter and certain others are, meaning a certain number is leaving. The difference is what is remaining inside this volume, right? So that is added to that volume, so it is increasing kind of. And then you have recombination processes would reduce the concentration inside, any generation would increase it. So this is what is called a continuity equation, and I can use this for a simplified form. So this is nothing but the divergence of this current from this volume, and I can write this in this differential form, and we will use this in the subsequent discussions. Okay, so we have two equations for electrons and holes. Now, how does the solar cell work? So solar cells under steady state illumination, and we can see that here. So you take a semiconductor piece and you're shining light on this, and this is under steady state. Steady state means with time there is no change. So that means that your dp by dt would be 0, no change with time, right? So this would be equal to 0. So then you can write your J is equal to Q integral of, or you can say this is 0. So essentially you can rearrange this equation, right? So that would be del Jp is equal to Q Rp minus Gp times dx. Okay, so I can calculate the current density Jp. Jp is nothing, J is nothing but the current density, current per unit area, and then you get this integral. Okay, so I can calculate the current density using this expression. So this is a very simple equation, and then what we can do is, okay, I can basically split this into right hand side into two terms. One is the generation part, okay, and this is your recombination part. Now, generation is very interesting because you have some light that is coming in. Let's say that light is fixed, okay? So you have some source of light. The intensity of photons coming in is fixed. So based on, and then we have seen how much of that light would be absorbed in the semiconductor. That can be calculated if you know the absorption coefficients at different wavelengths. And that depends only on the source as well as the solar cell design, right? So that we actually can be calculated, and that is represented by this JL. JL is the current density due to illumination. And of course, you have a loss of current because of recombination, and that needs to be calculated. So what we'll do is, if recombination rate is uniform throughout the solar cell, then I can say this is a constant. That's what my assumption is. So this comes out, and then this integral reduces to W. So J is equal to JL minus QWR. Okay, simple equation. Right, now what is the R? So let's take this. If only radiative recombination is present in the semiconductor, then we have an expression for R. Okay. So radiative recombination is expressed by this equation. We have seen that before. And this NP product also we have seen previously in terms of the quasi-Fermi levels. So I can then calculate the J from these equations, right? Using these equations. So substitute for NP, so this long equation here. So that gives you the R in the previous slide's expression. So R here, so we substitute that and we get this expression for the current produced. So you can see here, J is equal to this optically generated current, and then factors related to the radiative recombination. One thing that is interesting for us is this EFN minus EFP. We have seen that in a previous slide. So this is the split in the energy, quasi-fermilal for electrons, quasi-fermilal for holes. And this looks like a force, energy that drives this recombination process. Okay, so we will, of course, this is energy. I can convert that into voltage very easy to do. So I can set this to QV. QV is the voltage, and Q is the charge of an electron. And in electrical terms, so this energy can be expressed as QV, right? So this is an equation that you must be familiar with. This is basically an equation of a diode's current. So even though you don't see any diode here, so in a diode, that equation comes from recombination, by the way. Not really, because of there is a P and N part. That's an implementation aspect of it, but the basic theory is because of the recombination process. Okay, so this is a basic equation for the solar cell current voltage characteristics. Okay, so let's see what happens in that case. So if you take a solar cell, this is the equation, and we have the current density, so the J expressed in or plotted as a function of the voltage. And you can see optically generated current is this red line. So that's kind of constant. It does not depend on the voltage. But then you have a current loss due to recombination. So that is this factor. So this is like a diode. It is, very small up to a certain voltage, and then it starts to increase. In fact, there is an exponential increase, but the values would be very small, 10 raised to minus 13, and so on and so forth at low voltages. But it can increase to a few amperes at high voltages. So now, if I am an electrical engineer, I would really like to express this in terms of some circuit elements. So I can actually represent the solar cell this way. You have a current source which represents the optically generated current. This depends only on the intensity of the light and the spectrum, what wavelengths are present in the optical illumination. And the diode represents the recombination process in the semiconductor. And of course, you can connect a load to the solar cell. So this is your solar cell. Okay. So this is what is called a one diode equivalent circuit of a solar cell. Of course, there are some other components that should be considered, parasitic components that we should consider for analysis of solar cells. But this is a basic thing and a kind of ideal solar cell. But of course, we have seen there are two more recombination processes, OJ and SRH. So we need to add terms, the leakage, right? The recombination terms corresponding to those recombination processes. And you can see the expressions here. So we are actually writing QV by M KT. So this M is nothing but what is called the ideality factor that you must have, if you have taught this courses on diodes and so on and so forth, you know about this ideality factor. So the ideality factor MRAD is corresponding to the radiative recombination. So that is 1. And OJ recombination is 2 by 3. And for SRH recombination, there are multiple conditions. So what is called low level injection, I will not go into details, it's equal to 1. High level injection, it is 2, and so on. Okay. So modern solar cells will have mostly these three, and you hardly ever get into this kind of situation in a modern high efficiency silicon solar cell. Okay, so we have now understood how a solar cell works. If there are any questions, I can take a couple of them now before we go into look at what is the efficiency of a solar cell, what are the fundamental losses that defines the efficiency of the solar cell. Any questions?
Yes, sir. We have three questions from participant. I
Yeah,
think
please.
Dr. S. Rex is asking the question. Dr. S. Rex, you can unmute and ask the question. So I can read out the question, sir.
Yeah, please.
Photoelectric effect electrons will be emitted in the form of wave, that is radiation. Then how we are using this emission to load basics, kindly explain.
No, see, we are not, see, it's not a photoelectric effect. Yeah. So what we are seeing is not photoelectric effect. What we are seeing is a photovoltaic effect. So in a photoelectric, you have actually the electrons are emitted from the material, but here it is not emitted from the material. It's within the semiconductor. Okay. So this leads to a potential being created within the semiconductor, and that leads to, so the semiconductor is at a higher potential. So you can see the electrons and holes, electrons flow through the metals, for example. So electrons within the semiconductor at a higher energy than what you have in the load. Yeah. So the load and the conductors, uh, uh, so the energy of electrons here will be much smaller than what you have here. So hence these electrons will flow out, much like you have a tank, right, a water tank, and you are not emitting water molecules from this by adding more water, but it remains within the system. So photoelectric effect is different from the photovoltaic effect. Okay, we have not discussed photoelectric effect here.
There is one more question. How to identify lowest occupied state?
So this is a good question, and in fact, for solid state semiconductors, this is a easy thing to do. Meaning, of course, bottom of the conduction band is. Let me go to that slide. Okay. So we have the density of states in the semiconductor, right? So that is what you see here. And then you have a Fermi function. So what you get here, the density of states at equal to EC at this point is 0 actually. Yeah. But then it increases. So as you go up in the energy, the density of states increases usually as a square root of the energy. Okay. So there's a steady increase in the density of states as you go up. Now, the lowest occupied would be just above the conduction band edge. For all practical purposes, calculations, we actually assume this to be the bottom of the conduction band. Now, how do you determine this, the EC, EV, and this band structure? So that is falling back to theoretical physics, where we basically solve the Schrodinger wave equation uh, within the constraints of the material uh, uh, crystal structure. Okay, so I briefly alluded to that. So this is essentially here. You can see this is what is called the uh, the inverse lattice structure of the semiconductors of the kind silicon, gallium arsenide, and so on and so forth. Okay. But we don't, I mean, this is a little involved topic. So we will not, this is what is called a reciprocal lattice. We don't have much time to discuss that. This is actually fundamental solid state physics. So if from this you can actually calculate, you solve the Schrodinger equation within this, and then you can actually determine the. Of course, you need to know the spacing between the atoms and the electronic properties and things like this. Okay. So that you can apply the same methodology to any material to determine its band structure.
There is one more question from Kate Singh. How
Yeah.
to increase the lifetime of electron?
Okay, yeah. So that is, something interesting question. So we have seen the lifetime depends on. So we have seen this, right? The effective lifetime depends on three recombination processes. So if I want to have a very high lifetime, okay, so this has to be high, right? So then this has to be high, this has to be high, also this has to be high. So you can see here the radiative recombination lifetime is high, and it is determined essentially by the properties of the material. So we don't have much control on this. OJ recombination is also effectively decided by the material properties. What is in our control is actually the SRH recombination, which is dependent on the defect density in the semiconductor. Okay, so you can see the defect concentration increases, the carrier lifetime decreases. So you need to actually make higher and higher purity material, and in fact that is one of the things that has been happening in the PV industry. For example, till 2006 or so, PV industry was very small, and they used to use wafers rejected by the IC manufacturers. Okay. So uh, and that situation has changed in 2006, when the PV industry started using more high grade silicon than the semiconductor industry. Now actually, um, the PV industry uses almost 22% of all metallurgical grade silicon that is produced in the world, whereas the IC industry use about 2%. Yeah. So that is the situation. But about 15, 20 years ago, let's say, this was just the opposite. PV industry was using less than what the IC industry was using. So that has led to an industry where they could actually invest a lot of money into research to make very high purity silicon at very low cost. And in fact, that is one of the reason for us to get very high efficiency solar cells at low cost. Okay, so good. Thank you for the questions. If you have more questions, we can take it up after the remaining things. So we have looked at this. Now we'll see the fundamental losses in a solar cell. And this treatment, what we have seen so far, is somewhat very common for all solar cells. So we let's look at this fundamental losses. So we have a semiconductor, in this case silicon, let's say, and then we need to have a light source. So usually for characterization of solar cells, you go to a market and say, I want to buy a solar panel, right? And these people will actually sell you a panel, 500 watt, 2 meter by 1 meter, so 2 square meters. And now on what basis are they claiming that it is 500 watts? So there are some test conditions under which these solar panels have been measured. And this test condition is represented by what is called AM 1.5G. AM stands for air mass, G stands for global. Okay, so I'll not go into the details here. If we get time, we'll discuss that later. And you get about 1000 watt per meter square is the intensity, power density in this AM 1.5G. And there is also a spectrum, yeah, different wavelengths, how much they contribute to this 1000 watt per meter square. So you have this light coming in, Okay, and then if the photon energy is larger than the band gap energy, of course, the photons can be absorbed, and the electrons and holes get separated, and then they go much beyond the conduction band or below the valence band, and this excess energy is kind of lost to the lattice, the crystal, by collisions of these electrons and holes with atoms. Okay, so this is then called a thermalization process, because this will essentially heat up the crystal, and some part can just pass through the semiconductor, and especially if the photon energy is smaller than the band gap energy, that will not be absorbed, so those will actually just get transmitted. So that is lost. Yeah, you can't convert that into electricity, right? And then out of this generation, we have seen some losses due to radiative recombination. So there's some thermalization loss, but then even this energy is not completely preserved. A part of that is lost due to radiative recombination. So this light is escaping the semiconductor, and in some, there are some solar cells where people try to reuse those. So it's called photon recycling. We will not go into the details here. And that's important for solar cells made of perovskite, gallium arsenide, and things like this. And then you have Auger recombination, so there can be losses, and these are fundamental losses. Okay, you can't actually do much about them. Okay, of course, SRH recombination is another recombination process, but it's not fundamental. You can reduce, theoretically, you reduce the defect density to 0, and you will not have any SRH recombination losses. Now let's quantify this. So case of silicon is Eg is equal to 1.12 eV, and you can calculate the transmission losses is about 187 watt per meter square out of 1000 watt per meter square. So this is easy to calculate if you know the spectrum. Thermalization losses is about 328 watt per meter square. So you can see only about 485, more than half is lost already, yeah, by transmission and thermalization. So these are fundamental losses. You can't do anything about it. Radiative recombination losses about 162 watt per meter square is lost. So what is remaining is 32.3%, right? But if you now consider Auger recombination also, both radiative and Auger together, you would lose about 191 watt per meter square. So what you have remaining is 294. So 294 out of 1000, so 29.4% is the theoretical maximum efficiency of the silicon solar cells. Okay, so remaining thing, so that means 70.6% is just lost to these mechanisms. Now, this is under ideal conditions, so you need to basically design a solar cell to actually bring the efficiency close to this number. So we will look at the design aspects. I don't know if Dr. Sushil Kumar had addressed this issue yesterday, and we will quickly try to see some of those aspects. How do you implement the solar cells? It's very easy. So you have seen I presented the theory of solar cells without showing you any p-n junctions. Okay, so in effect, you don't really need a p-n junction to make solar cells. In fact, if you take a perovskite device, there is no p-n junction. Okay, and you can, they call it NIP, PIN, and so on and so forth, but there is no p-n junction, by the way, in the same sense as what you have in a silicon, a diode. Okay, so let's take this is your semiconductor, and you shine light, and the Fermi levels are split. You have a large number of electrons and holes, and then you put a barrier. So this is some material, maybe a dielectric with a large band gap, right? The bands are aligned so that the valence band of this dielectric is aligning with the valence band of the semiconductor, let's say silicon in this case. But here there is a huge barrier. It's like a wall. So the electrons cannot scale this wall. Okay. So you can see electrons that are flowing in this direction cannot come out through this. Okay. However, holes can easily come out because they don't face any barrier. So this is what is called hole selective contact. So selectively holes can flow through this contact. And on the other side, you put a barrier like this. So this is a electron selective contact. Electrons can freely flow, holes will not flow through this. Okay, if you have a system like this, you have a solar cell. Okay, now how do you make this? So there are hole selective and electron selective contact solar cells, silicon solar cells, where people use titanium oxide as electron selective contact, molybdenum oxide as hole selective contact, for example. So these kind of implementations are possible. But more widely, what you find is a PN junction type of device. So you have P-type silicon, and then one end you have a N plus silicon. So this is a PN junction. And then on the other side, you have P plus silicon. So highly P-type doped silicon. And by the way, this N silicon and P silicon can be either crystalline, polycrystalline, or amorphous silicon. So different variations are there. And you can see the equilibrium band diagram. So in this case, electrons can flow very freely onto this contact, right? N plus silicon, but holes cannot, because there's a huge barrier. Here, there is a small barrier for electrons, holes can freely flow. Okay. So this is one way of implementation, but this is not the only way. Now, how do you design the solar cells, right? So there are practical designs. Two of them are shown here. One is the aluminum back surface field ALBSF solar cell, or passivated emitter and rear contact solar cell PERC. And what you see here, look at this. So you have a thick P-type silicon, crystalline, okay? And on the front side, you have a texture, which means that the surface is quite rough. You see these pyramids, okay? And the pyramids are required to reduce reflections. And then you have a N plus silicon, a PN junction is formed by diffusing phosphorus onto the surface of the silicon. Then you deposit a silicon nitride layer on top. So this is what is called an anti-reflective coating, further reduce the reflections. And then on the front side, you have the silver that is getting contacted to the silicon through this, the ARC layer. And on the back side, you have aluminum making direct contact with the silicon. So there's something, a BSF, essentially, aluminum we have seen is a P-type dopant. So some of this aluminum will dissolve in the silicon, making this layer close to the aluminum, this silicon layer, heavily aluminum doped. So that is a P plus layer. So that looks like this. This is your P plus aluminum BSF. This is your front side junction, right, in this solar cell. Here, PERC, the only difference is everything else here is all same. Backside, there is some difference. You have a aluminum oxide silicon nitride layer deposited on the entire backside, and then you open small windows by laser ablation of this dielectric. Then you put aluminum on the backside, and the aluminum make contacts through these windows, the openings in this aluminum oxide silicon nitride stack. So this essentially provide higher efficiency than this, because the backside is not very well passivated in this case, because this backside is directly in contact with the metal, where the surface passivation is very poor. And instead of that, here you have an interface between the semiconductor and the dielectrics, aluminum oxide and silicon nitride. So that provides very good passivation. This area, this contacts, the area would be about 1 to 2% of the total backside surface area. So as a consequence, you get much higher efficiencies for this PERC kind of solar cell. So now you have understood the basic components of a silicon solar cell. So you have this front contact, silver, right, back contact, and then you can make connections to take the current out. Now, for the solar cell design, optical management is very important. This is the AM 1.5G spectrum that I mentioned. This is the energy flux in watt per meter square per nanometer, and this is the wavelength of light. Of course, this extends to much longer wavelengths, but then we are interested up to 1200 nanometers, because that is what the silicon can actually absorb. I think we will skip this part. Oh, yeah, maybe you can see that the absorption coefficient is very high for short wavelength light, right? This is UV, for example, and then visible range also get absorbed within a very short distance. This is the thickness of the silicon wafer in meters. So this is about 160 micrometers. Okay, so within a few micrometers or tens of micrometers, this visible light get absorbed, and infrared, you can see as the wavelength increases, not all of that light actually can be absorbed in 160 micron thickness of the silicon wafer. Why 160? Because that is close to what is being used in the industry today. So industry currently use about 130 micrometer thick silicon for making solar cells. So if you have this kind of situation, you need some way to actually confine the light within the semiconductor. You don't want to lose this to transmission, because that will reduce the efficiency of the solar cell. So what do we do? So one of the first tasks in the solar cell design is to ensure that all photons with energy greater than the band gap energy is absorbed by the semiconductor. So one problem is, of course, surface reflections from the surface of the semiconductor, and that can be calculated if you know the reflectivity, meaning the refractive indices of the semiconductor and air. So that is known, and you can do the calculation. So usually you get reflectivity if you have a silicon surface which is very smooth. More than 30% of the light would be actually reflected back. Okay, so 30% is very large number, right? We don't want to lose all that light. We want to convert it into electricity. So what do we do? So you can then reduce the reflections by introducing this kind of structure. So the pyramids. So I have shown that on previous slides on the front side of the solar cell. So these pyramids are actually, it works like this. About 35% of the light gets reflected from a flat surface. Now, if you have a pyramid, the light is incident on the facet of this pyramid, and then 35% gets reflected. But this reflected thing actually falls on the next pyramid. Okay, it does not go back to air, right? Just falls on the next pyramid, and then only 35% of that actually get reflected. So the effective reflection is 0.35 square. So that is about 12%. Yeah. So from 35%, we reduce the reflections by creating this kind of pyramids to about 12%. So, but of course, there are some disadvantages. This are texturization. This is called a texturization process. Can be very easily done by basically dipping silicon in potassium hydroxide or sodium hydroxide solutions. Now, if you want to reduce this further, what you do is you use anti-reflective coating. So the idea here is to use what is called a quarter wavelength anti-reflective coating. So you have reflections from the surface. Yeah, this is your ARC coating, and this is air, right? So at this interface, there will be some reflections, but then light goes through, part of the light goes through the ARC layer, get reflected from this interface between the ARC and the semiconductor. And these two rays should destructively interfere. Okay, so then you can reduce the reflections to nearly zero. So that is what is being done here. So you can see the thickness of this ARC layer has to be chosen as 1/4 of the wavelength divided by the refractive index of the ARC layer, and refractive index of the ARC layer has to be chosen as square root of the materials on both sides, in this case air and the silicon. So if you can see the minimum reflectance at in such a design, 650 nanometers, if you want that, then with a refractive index of 1.96, a thickness of the film. So this is usually silicon nitride. Okay, you can use 83 nanometer silicon dioxide to basically reduce this. So using these two techniques, the reflections have been brought down to less than 2%. Yeah, in solar cells. You can see that here, the results of some of this work being done at IIT Bombay. So as cut wafers, yeah, when you make these wafers, the reflections are fairly high, more than 30% that I already talked about. And then you actually have the after texturization, okay, and it comes down to about 13%. And after deposition of the ARC layer, it comes down to about 2.5%. Trapping of longer wavelength light, I mentioned that infrared can actually just escape from the backside. And to prevent that, we have a texturization also on the backside. So what happens in this case is that you get total internal reflections because of the high angles at which these rays get refracted at this kind of interfaces. So you can see the light is entering here, and then it get diffracted in going like this. Then it bounces back to here, and then here, and so on and so forth. You can see this. So you can get close to 50 such bounces within the semiconductor. So instead of one pass, so let's say this is 100 micrometers. If you have, it goes through once, so you have 50 micron, meaning 100 micron, right? But if you are able to bounce it around 50 times, then effectively you have increased the thickness, meaning optical thickness of the solar cells to 5,000 microns, right? 50 into 100, so 5,000 microns. So with that, you can actually get very good current and efficiency. You can see that no light trapping, the short circuit current density can be very small, but if you actually create structures to trap the light inside the semiconductor, you can get very low, meaning very high currents and hence efficiency. Thickness of the semiconductor, it is decided by what is called the diffusion length. I will not go into the details here. And surface recombination reduction that we have seen. So chemical passivation, field effect passivation. So examples are, for example, we have seen on the PERC, the backside, we have back surface field, but also we use silicon nitride as ARC, anti-refractive coating, which actually contain positive charges. So this can actually affect some field effect passivation. Aluminum oxide contain negative charges and good for passivating p-type silicon. And chemical passivation is basically heightened passivation of the surface. So this comes in silicon nitride if you use plasma enhanced CVD methods for deposition of the silicon nitride, or amorphous silicon. There are solar cells using this. Okay, so for solar cells, so today's solar cells all have more than 20% efficiency. So excellent surface passivation is very, very important. Okay. The other is now we need to worry about how to take the current out. So there is a distributed conductor network. So the silver is actually making contact. So all these white lines on this top or gray lines, so to say, are really the silver, which is collecting current from all over the solar cell surface. So it's very important to actually design the width of these lines properly and the spacing to obtain optimal performance. Okay. So we have series resistance. So the series resistance can come from this metal, the contact of the metal with the semiconductor, and so on and so forth. So you need to keep this, the parasitic resistance is very, very small. You can see the numbers because the solar cells that we are talking about are very large area devices. So this is the data for 5-inch by 5-inch silicon solar cells. But these days, people are making 18 centimeter by 18 centimeter. So that's about how much? So 2.54 for 7-inch by 7-inch kind of devices, right? So they actually will produce about 14 amperes of current. Yeah, here it's about 5.5, 14 amperes of current, and hence your resistance has to be very, very small. So 1 milliohm to 10 milliohm, already there is a substantial decrease in the power output. So this is the current voltage characteristics of the solar cell. And if you increase the series resistance, it actually degrades the performance. This is power is a product of the current and the voltage. So that would form a shape like this. You can see the maximum power reduces drastically. So if you look at the electrical circuit, you need to then add a series resistance. Okay, and two diodes are shown here. So mainly this was what I showed previously, where we talked about the radiative recombination, but then you have other recombination process. So you, for every recombination process, you add a diode. Okay, so this is a typical equivalent circuit you see for solar cells in the literature. And there's also shunt resistances. So you have a PN junction, for example. The junction can be shunted by various problems during processing of the solar cells, also during field deployment and so on. So you need to add then a shunt resistor, and the shunt resistance need to be actually very high. Ideally, this should be an open circuit, right? So it has to be very high. That's a very important consideration. Now, the PERC and aluminum BSF technology is now completely outdated. There is still some manufacturing of PERC solar cells, but more importantly, the TOPCon and HJT devices that I'm going to show you are the technologies that are currently in production mainly. And going forward, some advanced versions of this would actually also come into picture. Now, what is the difference here? So you take the substrate is now N-type silicon, not P-type, unlike in PERC. And then you have a P diffusion. So boron is diffused to make a P-N junction. Okay, and then you have on, of course, on the front side silicon nitride, but also aluminum oxide to passivate this P-type junction. On the rare side is more interesting. You have a silicon dioxide, very thin, 1.5 nanometers or something, so that there is some tunneling current through this. So current can flow through this. Silicon dioxide is an insulator, so you can't use thick silicon dioxide. It has to be ultra thin. And then on top of that, or below that in this schematic, you have N-type polycrystalline silicon, which is deposited. And then you have contacts, silver contacts on both front and back side. So this provide very good passivation of the rear side. You can see light can also enter from the back side as well as from the front side, right? So this is what is called a bifacial solar cell. And the efficiencies can be in the range of 24 to 26%. And this is what is being manufactured mainly these days.
Sorry, sir.
Yeah.
Sir, next speaker has come. So
Yeah,
should
yeah.
we
I'll
conclude
close
within
this.
2 minutes?
I'll close this
Okay.
in 1 or 2 minutes.
Okay.
And then you have advanced TOPCon technologies where you actually have some modifications of this, and the efficiencies can be increased to 28% up to. So 27.8 has been demonstrated, using this. HJT is another technology. Instead of using polycrystalline silicon, where they use amorphous silicon. The advantage of this is that this technology is this kind of solar cells are made by using low temperature processes. So the thermal energy used for making the solar cells are very low. Okay. And now this is the next version. In fact, a lot of research is going on in this. Both the contacts are brought to the back side. Okay, from the front, you take it to the back side. So this is the what is called interdigitated back contact cell, and that may be the future. Currently, this is an expensive technology, but with time, I think this will also become commercially viable. Okay, that's it from me. Any questions? If you have time, I can take some questions, or depending on the organizers. Thank you very much for your attention.
Participants, if you are having any question, please ask. We will take a question answer session for 2 minutes. If you are having any question, please unmute yourself and please ask question. Okay, sir. On behalf of management, principal, and Atal FDP organizing team of AC Patil College of Engineering, I express my deepest gratitude towards Professor Anil Kattantharayil, sir. Sir, your talk will greatly benefit researchers and professionals in exploring their ideas, as you have covered the basic fundamentals of design of solar cell. Sir, thank you very much. We request you to share PPTs. Will you please?
Hello? Okay, thank you. I think I'll stop sharing, right? That's what it is. Okay, I'll sign out now. Thank you very much.
Okay. Thank you, sir. Thank you so much.
Thank you so much, sir. Thank you.
Bye bye.
Okay. Amal Patil, sir, will you please stop recording?